Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field everywhere. So to begin, we need to write down Gauss's law. The closed line integral, or the closed looped integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals kq, total charge inside, divided by r squared, the distance away. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, and it is equal to 1 divided by 4 pi epsilon naught. Okay, so let's find the electric field. All right, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then Q is 0, so the electric field must also be equal to 0. So 0. What about in between our first shell, A to B? Well, remember that in a conductor, the total electric field must be 0. So there's no charge on the inside, nothing's induced. E must also be 0 here. B less than R less than C, we're in this first voided region. Our inner shell has a total charge of plus 2q, and so that is what would be Q enclosed here. So Q enclosed is plus 2q. So that means that the electric field can be written as a point charge in terms of epsilon or just as k. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2q, divided by r squared. There we go. And let's see now, C less than R less than D. So now we're in this outer region, okay? So if we're in this outer region, I know that electric field must be equal to 0 here in this region, because when we're in a conductor, the net electric field must be 0. I have plus 2q here, so I need minus 2q on this inner surface. But in general, E still must be equal to 0 there, because we are inside of a conductor. And finally, when we are outside of this system, all you have to do is take the total charge, minus 4q plus 2q is minus 2q. So Q enclosed is minus 2q. And we get E equals 1 divided by 4 pi epsilon times minus 2q over r squared. All right, we can go ahead and graph this. And what do we see? 0, 0. So this is 0 here, 0 there. Between B and C, we see 2 over 4 pi epsilon 0 r squared, so something like this. And now we have to remember one of the properties. So even though that this is a quadratic function, you can get out your graphing calculator and see what happens when you have a negative value outside of your expression that you're working with. So I'm graphing it now, and I think that all of you should graph it as well to see what happens when you have a negative sign outside of the expression. So it looks like we do something like this. Or more, oh, excuse me. When you graph it, there will be two solutions. Make sure that you choose the physical solution. And so in this instance, it will be something like this. All right, There we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small, remember, electric field must be 0. There's nothing on the very, very inside of this guy where that green dot is. So this guy must be 0. What about on the outer surface? Outer surface must be the total charge on this shell, plus 2q. Okay, let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge from this inner shell. So we need a negative 2q on that inner surface. Okay, and then what about on the outer surface? Well, on the outer surface, all that you have to do is think about, okay, well, there's minus 2q right here. What has to be out there? Minus 2q. That's the only way for the net charge to be like this. So it has to be minus 2q. There we go.